Hi, my name is Will Krawczyk, Scientific Services Manager at Chemical Computing Group. Today I'd like to demonstrate the tools that we have in Mo for fragment-based drug design. As part of this session, we'll look at scaffold replacement, where we seek to change the central core of a ligand whilst preserving the remaining chemical groups. As part of this session, we'll also look at pharmacophores and their role in fragment-based drug design. So let's get started. So I'll start by using the Open button to retrieve the file that we're going to be working on today from the sample mol directory. The file is 1kv2. I'll go ahead, select the file, and click OK, and I'm greeted with this Load PDB file panel, which allows me to select what data we're going to load into Mo. Here I'll accept the defaults and just click OK, and we see the structure appear in the main Mo window. Notice the structure is coloured by its secondary structure, so we've got our beta sheets in yellow, helices in red, and the turns shown in blue. Before we can start thinking about scaffold replacement, the very first thing we need to do is prepare our model. Given that this is a raw PDB file, it typically won't have any hydrogens or charges included. Perhaps there are also some missing loops. So we need to address these issues and ensure we're working with a high quality model. Unfortunately, Mo has an automated preparation wizard called QuickPrep to help us with this task. The panel comprises three main sections. The first, handling preparation and cleanup of the structure. Second, sets tethers and restraints. The third handles refinement. I'm just going to accept the defaults here and click OK to start the calculation. I get a message at the top left of the main Mo window which gives me a progress update. Now I'd just like to take a moment to reopen that panel to explain what's going on in the background. The first preparation stage ensures that we have a complete model. Here we're adding in missing hydrogens, charges and side chains. If there are any missing loops in our model up to 10 residues in length, these will be modelled and added in. Protonate 3D optimizes the ionization states of bound molecules and their side chains. It also generates a hydrogen bonding network through the placement of polar hydrogens. By default, we tether our atoms within the active site. We do that to ensure that the original geometries of those atoms as captured by crystallography are retained and we don't lose the geometries of those atoms to processes such as energy minimization. Likewise, we fix any atoms that fall outside of the active site, and we can do that for reasons of computational efficiency. The final step is the refinement stage, which performs an energy minimization to ensure that we don't have any clashes in our structure. I see that the calculation is complete. The message has gone from the top left of the main Mo window. That tells me that our model is now prepared, so I'll just cancel this, and then I'd like to get a better view of the ligand's interaction with the receptor environment. For that, I'll use Site View, which isolates the ligand together with any residue within 4.5 angstroms. Next, I'd like to introduce the System Manager. I'll just pin that to the main Mo window as a means to control all of the data that we have in our system. From here I can hide and show different atom sets, I can make selections, I can also render and generate surfaces. I'll just use the System Manager to hide the ribbon, and I'm going to colour the ligand a bright colour to ensure that it stands out. And with that, our system is now ready for modelling. But before we get into changing the central core or scaffold for better interactions with the receptor, we first need to understand the existing interactions between this co-crystallized ligand and the receptor environment. The first place I'll look for that type of analysis would be the main Mo window itself. Mo has automatically calculated and annotated the classical hydrogen bonds, which are shown by these dotted lines with a cylinder in the middle. The size of the cylinder gives me a clue about the strength of the interaction. The longer the cylinder, the stronger the bond. Mo can also calculate non-standard interactions such as proton-pi, halogen and sulfur interactions. If I want to build a picture to understand which residues we're interacting with within the active site, I can go ahead and create a ligand interaction diagram. This raises a 2D schematic of our ligand together with the interacting residues. There's a key at the bottom that helps me understand this graphic, but in brief, the green residues represent those that are greasy or hydrophobic, purple residues represent those that are polar, The blue cloud indicates that the ligand is exposed to solvent. The dotted line represents the binding pocket. And here I can use this diagram to analyze the key interactions on the central portion of this scaffold which we'd like to replace. I'm less concerned about the fragments on either side. It's the scaffold that the central portion of the scaffold that I'm interested in, and here I can see that we have specific interactions with the urea group or the carmamide. We can consider preserving these key interactions through use of a pharmacophore when we generate our new scaffolds. Beyond this 2D analysis of the ligand-receptor complex, we can also look at this in 3D by generating a surface, and you'll notice some of the default surfaces that we have available within Mo. I'll generate a receptor surface which is coloured by atom colour, predominantly grey representing the carbon atoms, but we also see blues and reds corresponding to the nitrogens and the oxygens. This surface type is useful in identifying hydrogen or potential hydrogen bonding opportunities. We see those shown by white patches, such as the one deep in the pocket here. We also have, so the white patches represent the polar hydrogens, whilst lone pairs are shown by these cyan patches. So these are clues for potential interactions we could pick up with a modified scaffold. So just to recap, we've analysed the contacts in the main Mo window, we've looked at the ligand interaction diagram and used a receptor surface to gain valuable information on the interaction between ligand and receptor. We've identified the existing hydrogen bonds, which we can use when we code our pharmacophore later. So now that we've prepared and analysed this complex, we can go ahead and replace the central core of this scaffold. I'll just clear the surface before we do that, and then I'll go ahead and launch the scaffold replacement panel. So we find this within the Fragments tool, and we have multiple options when it comes to scaffold replacement or fragment-based drug design tools. I'll select the top option here, Scaffold Replacement, which opens the panel comprising 4 main sections. At the top, we can define our system in terms of ligand and the receptor environment. In the second portion, we can define the type of operation that we'd like to perform, and here you'll notice the same options that we saw earlier within the compute menu. The third section allows me to filter or add pharmacophores to preserve key interactions, and the final part handles refinement and scoring. So for our scaffold replacement operation, we're going to generate new ligands by replacing a portion of the ligand whilst preserving a portion of the remaining chemical groups. The panel is actually guiding me what to do next, so it's saying to select the heavy atoms of the scaffold to replace. I find the most convenient way to select atoms is to raise a 2D schematic of our ligand, and then I can simply go ahead and select the atoms that we'd like to replace. We see that they're highlighted with a green halo in the main Mo window, with these green arrows representing the attachment points. The panel itself explains that we're going to be replacing the 15 atoms between the 2 exit vectors. Beyond that, we have some default descriptors, filters that have been added related to a molecular weight cutoff, a TPSA range, and a note on reactivity. These descriptor filters can be customized, removed, and we can add more. It's a very efficient means to rapidly filter our results. Any of the descriptors across the whole suite of Mo can be used here, including smart strings, which we can use to define groups that should or should not be present in the structures. I notice here that the Check Filters button is coloured red, and if I just hover my mouse to raise bubble help, it tells me this button is coloured red if the ligands do not pass the descriptor filter. If I click this button, it gives me more information at the top left, showing me that the molecular weight of the existing co-crystallized ligand is 528. Given that the descriptor filter that's been added by default has a molecular weight cutoff of 500, this is telling me that the current co-crystallized ligand would not pass that filter. For that reason, I might want to consider upping my threshold, so I'll manually type that as 600, and I'll start our first run by clicking search. In the background, Mo is now searching for scaffolds to replace the atoms in the halo between the bond vectors, whilst preserving the geometry of the fragments outside of the bond vectors. A database viewer is opened where the results will be populated, and we see a progress bar at the bottom of the panel so that I can keep track on this calculation. In the background, Mo is searching a conformational database which contains a little over 40,000 linkers and fragments. We do have access to larger fragment and linker databases which are available for download. The results themselves are displayed in the database viewer, our main window for viewing results, database entries, and from here we can also jump into various tools that we have in Mo, such as QSAR. The database viewer itself looks and feels much like an Excel spreadsheet, but if I just drag this mol field open, you see that it actually contains the 3D structure of our ligands. I get an RMSD readout, together with info used to generate these structures, plus some predicted properties. Beyond analysing the quantitative data, I can also analyse new scaffolds in the receptor environment, and for that, I can leverage the database browser. I can use this to view conformations of our scaffold, both in 2D here and the 3D environment, one entry at a time. I'll just deselect the atoms, so here we see that the replaced scaffold, the newly generated scaffold, is shown in green against the original co-crystal scaffold, which is shown in magenta. Using the browser, I can then click through one entry at a time to look at each of these newly generated scaffolds within the receptor environment. Although appearingly we've achieved our goal of replacing the scaffold, if I have a closer look at some of these results, I see that not all of the key interactions are preserved. Here, the green scaffold, the newly generated scaffold, does not honour that original H-bond that we see with the magenta-coloured co-crystal ligand. If I look at the database viewer, I see that we generated 175 entries, so perhaps I'm a little spoilt for choice, and what I can do is go back and define and preserve some of the key interactions and do a second run to help place our scaffold. So for that I can use a Pharmacophore, which is a 3D model used to describe the type and the location of the binding interactions between a ligand and its target receptor. In the context of scaffold replacement, this will ensure that the scaffolds we generate preserve key interactions and improve the quality of the structures that we generate. I'll just close our database viewer, and I'll go down to the Pharmacophore part of the scaffold replacement panel, and I'll click to open our Pharmacophore Editor, which allows us to add, remove, and modify query features from either the receptor, the solvent, or the ligand. The features that we create will soon be populated at the center of this panel. Notice that the main Mo window has been updated with these annotation points. These are color-coded such that the acceptor annotation points are shown in cyan, donor annotation points are shown in magenta, aromatic in orange, and hydrophobic in green. You'll notice that some of these annotation points don't sit directly on the ligands, so these are projected annotation points and give us an idea about directionality. We can use these annotation points to create Pharmacophore features and ensure that the ligands we generate preserve the important urea H-bond interactions. So I'll go ahead and select one of the annotation points and create a feature from that. It might be useful to add a second Pharmacophore feature on the opposite side of our ligand, but here I can see we've got two projected annotation points. I can see that they don't quite meet the receptor environment and the specific residue that they're interacting with, so for that reason I'm going to toggle off my ligand annotation points and toggle on my receptor annotation points. That will allow me to select the specific annotation point of interest and generate a feature there. So that's it. We've generated our Pharmacophore. I'll just turn off the annotation points and then I'll go back to the scaffold replacement panel. So next I'm going to reselect the scaffold. I'll just go ahead, raise that 2D schematic and select exactly the same atoms as before. So you'll see again, we're selecting 15 atoms with the 2 exit vectors. I do have the chance here to change the name of the output database where the results will be written to, but here I'm just going to click search and I'll choose to overwrite the existing results file. Like last time, Mo is now searching for scaffolds to replace atoms in the halo, between the 2 bond vectors, whilst preserving the geometry of the fragments outside of the bond vectors. But unlike last time, we're using a pharmacophore to ensure that the key interactions are respected. As we did before, we can inspect the properties of our novel ligands using the database viewer, and I can also browse to have a look at these both in 2D and 3D simultaneously. I'll just minimize our 2D viewer and deselect the atoms. Again, we see the newly generated scaffold shown in green against the original co-crystal ligand shown in magenta. Again, I can browse through these, and this time I see that we generally have less results within the database viewer, but they're of a higher quality in the sense that as we click through each one of them, we see that they all respect the key interactions that we originally had with that co-crystal ligand and the receptor environment. I'll just close the browser and just bring back our scaffold replacement panel to wrap up today's session, where we explored how to replace the central portion of a scaffold whilst preserving specific chemical groups. We then repeated the exercise using a pharmacophore to preserve key interactions and improve the quality of the structures that we generated. I hope you've learned a lot today. If you have any questions, please do reach out to me at support@chemcomp.com.